Okay, given the function f of x equals x squared plus 2x plus 10, write an expression for the slope of the secant line that goes through the points minus 4 and 18, and also a nearby point, minus 4 plus h, and f of minus 4 plus h. So remember, this idea of a nearby point, of course, depends on what h actually is. We're assuming h is not going to be exactly 0, of course, for a secant slope, but if h is fairly small or fairly close to 0, we can get our 2 points pretty close together, and the closer they are together, the better the secant line will be at approximating the slope at exactly minus 4 and 18. And that's essentially what parts B and C are dealing with in a few more moments here. Okay, so we have to recognize we have 2 ordered pairs, and this first one is not causing too many problems I wouldn't expect, so it's just minus 4 and 18. It's the second ordered pair that's fairly abstract due to that h that's attached to our minus 4 there. So remember, h is the difference between our two x values. That's all that means. So before we maybe deal with the minus 4 plus h, let's make sure we can understand where the 18 came from. And I'm sure you do, but just as a bit of a review, remember, if we input an x value, in this case minus 4, into this function, we have to square that input, and then we add on twice that input, and then plus 10. And this is going to give us 16 minus 8 plus 10, which is 8 plus 10, or 18, precisely what it should be. That's the y value of our first ordered pair. So we just have to keep that in mind when we try to find our second y value. So let's get rid of this. It's just there as a refresher course. So the second y value is going to be a little bit more demanding, and before we deal with that, let's get some space here. Deal with that later without entirely forgetting about it. Okay, so let's get our second y value, which means we have to get a pen, and we have to put in minus 4 plus h into our function here. I'm not sure why I'm doing it up there again after I made the space. Let's do it here. F of minus 4 plus h. We have to input minus 4 plus h in this quadratic function. So we have to square it. We have to add 2 times that input. And don't forget, we also have to add on 10. And I'll write it as minus 4 plus h, but h subtract 4 works as well. Same thing. So we have to square that binomial, and that's going to be minus 4 squared. We'll have a pair of minus 4 h's, which will be minus 8h, and then h squared. And then we'll have 2 times minus 4 as we expand this. This is minus 8, and then we'll have 2h, and then finally little old plus 10. So that means our f of minus 4 plus h, which isn't our secant expression yet. We're just getting that second y value, which is the annoying part of this question. We can just do some simplifying here and realize I have like terms there. And I can just maybe sort some things as well. So let's start off with the h squared value. We have minus 8h plus 2h, which is minus 6h. And then in terms of constants, we're getting some deja vu there. We have 16 minus 8, which is 8 plus 10, which is 18. And that's exactly what we want to see, because when we subtract those two y values, we want to see our constant disappear. Okay, so there is our, and I guess I might as well make a little bit more space before we deal with our expression for our secant slope. That should be enough. Okay, so how do we set up our expression now? Maybe just in a separate color. We'll say the slope of our secant slope is, of course, just y2 minus y1 all over x2 minus x1. And now you can see why we really needed that second y value, which we have in light blue. So let's put it in light blue. There's our second y value, which is the output after inputting minus 4 plus h. It is h squared minus 6h plus 18. And then we can subtract our other y value. I guess I can subtract the h's on the bottom as well. So what do we got? Our other y value, of course, was also 18, and that's awesome because those will disappear once we subtract those in the numerator. And then down below, our second x value. Remember, this is not really necessary, but I'll do it in this first example at least. There's our x2, and then when we subtract our x1, we're going to have to subtract a minus 4. And remember what always happens in the denominator? You should be left with a h, which of course is the case here. So we can squeeze in one last time, one last step, I should say. Our numerator is just going to be h squared minus 6h, and on the bottom, minus 4, subtract a negative 4 is just minus 4 plus 4, or 0, and we just have our h in the bottom. And remember what this thing is? This is our rise over our run, of course, for our secant line involving two separate points. Okay, and that's that. We got our expression. Now we'll move on to part B, where we're being asked to basically use this expression and also maybe clue in as to what the h is actually accomplishing for us. So we have to sub in 2 for that h. And I was going to use h squared minus h over h, but we can simplify that as well. Maybe we'll just do it in the space here in white. If we factor in h out of the top, the numerator of that secant slope, we can divide that h in the bottom with that h in the top. So I mean, because now I have to sub in 3 h values, and I guess I could substitute 2 in the h squared minus 6h divided by h expression, but that's a little bit too much work. All we really need to use is the simplified h minus 6 formula. And you can use either or, and you'll see in the answer key that I actually used the long-winded one there, and the reason for that we'll discuss when we get down to part C. But for finishing off this question, all we really need to do is evaluate the simplified secant expression, which is h minus 6. We're going to evaluate that. That's what this vertical line means, incidentally. Also, you'll see this in the answer key. And I better not say x equals 2. Better say h equals 2, because there's no x's in that expression. So this is just this vertical line notation saying, can you just evaluate that expression when h is 2? And hopefully you say, sure, that's easy. We'll go 2 minus 6, and that gives us our first secant slope, which is going to be minus 4. So there's the first part. Now that simply means when our 2 points are 2 units apart, that gives us our secant slope, and you can probably imagine that's not a great approximation of your tangent slope. So let's do the second one. We'll evaluate h minus 6 at h equals 0.2. And then I just have to go 0.2 minus 6, which I guess I can write out. 0.2 subtract 6 gives us negative 5.8. Now our two order pairs are pretty close, only 0.2 units apart in terms of their x values, and that gives me a little bit more confidence, I guess, in understanding what my tangent slope is. It's probably around minus 5.8, and to get an even better idea, we'll go to the third part. We take our h minus 6 expression, and yes, we substitute in h equals 0.02. So now those two order pairs are really close together. Notice they still haven't coincided, of course, but when it's h is 0.02, I guess we'll substitute it in here. We're going to get a negative 5.98. So I think you can probably guess what's happening. Smaller h gets, closer this number seems to be getting to minus 6, which means when we go ahead and take a look at limits here to finish this problem off, we should expect to get a tangent slope that's exactly minus 6. Okay, so let's go ahead and we'll find the slope of our tangent line. Make sure we remember it is the limit, or it involves the limit of our secant slope. And what happens in the limit? Well, we want to let h go to 0. Sometimes I say get smaller, but that's not entirely true, because negative 10,000 smaller than negative 1. What I really mean is make it go really close to 0. And remember, when it gets close to 0, the 2 points get closer together. And that's the conceptual significance there, I guess, or the awareness that you need to have when you're working with this. So if we set up our limit of our secant slope, of course, we're going to use that algebraic expression. Now, earlier I said, you go ahead and simplify that down, but I'm not going to do it, simplify it down to h minus 6. But I'm actually not going to do it when we set up our tangent slope, because I want you to be aware of what always happens when you do your rise and your run and you try to let h go closer to 0. Remember, you always get your indeterminate form. All right? And of course we have that here. If h goes to exactly 0 right now, we'll have 0 squared minus 6 times 0, which is 0, divided by 0 on the bottom clearly. And that indeterminate form is just a fact of life when you're working with secant slopes when h goes exactly to 0. So what you have to do is get rid of that h on the bottom. Of course, that's what we did when we were working with that expression. We're going to do it again just to make sure we're clear. So I'm going to factor out an h on the top, h minus 6. And then I can divide by an h on the bottom. That can go directly into that h on the top. And here we have our limit, which remember, of course, is going to be our tangent slope. So the limit as h goes to 0 of the expression h minus 6. Now when I let h go directly to 0, I get 0 minus 6. I'm not getting indeterminate form, so that tells me we're on the right track. So let's finish off, and I will actually be really clear on this wrap up. Maybe too clear. We'll substitute h equals 0, because when h gets to closer and closer and closer to 0, h minus 6 gets closer and closer and closer to minus 6. And I'm actually going to make sure that is ridiculously obvious. This is what's going to happen via our limit, which gives us a tangent slope of exactly minus 6. Now the weird part is our points aren't really aren't coinciding. They're just, we know what's going to happen if they were able to coincide, because remember, it's still based on a secant slope. That's pretty abstract, but just remember, the limit is saying as the distance between those 2 points goes to nothing, we know the slope of this tangent is going to get closer and closer and closer to minus 6, so we can be confident that this is the slope of our curve, our tangent slope, at that ordered pair, which I've long since forgotten. What was it? Minus 4 and 18. So at minus 4 and 18. And sometimes the x value is all we're really worried about. We could also say tangent slope at x equals minus 4. So there it is. There's our first example. Have a look at it. It's a great example because once we get our our secant slope set up, our expression for that, whether you reduce it or not, you get to see your h in action, and you get to also see the smaller, the closer h gets to 0. I think it's pretty obvious if we look at our secant slopes at minus 4 and minus 5.8, minus 5.98, that it looks like they're getting closer to minus 6. And the limit business that we did here is the rigor that's required to not just say, I think it's minus 6. It actually mathematically demonstrates that it is exactly going to be minus 6.